Hey, today we're going to be solving this composite beam for the stresses that occur in the beam. We're going to use a method of transforming the beam. We have this beam. It's wood and steel. Obviously, it's been joined together, so it's transferring stresses between the two materials. So it's behaving as a composite beam. And so the methodology that we're going to choose in resolving this is we're going to convert the wood to an equivalent amount of steel, deal with the transform section, figure out what the stresses would be in that steel section, and then convert them back to the components that are wood as to what they would be in the wood. So this is not all original work. I want to give credit where credit is due. So I've taken this from example 6.17 in the Ebler Mechanics Materials textbook. I wanted to use the textbook because they've got some incredible images. And so that's going to make our visualization of what's going on a little bit easier, being able to use those images. So with that out of the way, let's get into it. We have a few givens. We have a moment. And we have our elastic moduli for wood and steel at 12,000 and 200,000 megapascals respectively. So the first thing we have to do is we have to transform the section to all steel. And to make that easier, what I want to do is I want to be able to get the transformation factor or ratio, and we're going to use our neta, and we set that equal to the elastic modulus of the material that you're transforming from to the elastic modulus of the material you're transforming it to. So in this case, wood to steel, so wood over steel. And so we'll have 12,000 megapascals all divided by 200,000 megapascals. And we get a transformation factor of 0.06. So now we can use that to basically change the width of the beam over the wooden component so that it would be the equivalent amount of steel to get the same capacity. And so to do that, we're going to use B steel, and I'm going to give it a prime to indicate that it's part of the transformed component. And we just use our transformation ratio and we multiply it by the original width of wood. And so if we do that, 0.06, and our width of wood from the cross section you can see is 150 millimeters. And we end up with a new transformed width of 9 millimeters. So with that, I'm just going to go bring in one of the images from the textbook so you can see what the transform section looks like, so you can see what we've done, because that's what we're going to work with for the next little bit. So let me go get that image and I'll pop it right in here. Okay, so there you go. You see what this equivalent beam would look like if it was made of all steel. So you see the wooden component is now like this steel web. We can go on and carry on our calculations doing that. So the next little bit should look very familiar to you. It's as, if we were dealing with this inverted T-section, there should be no differences from what you're used to. And it's only when we get to the other end of it that we'll have to convert them back to the original cross section. So let's get on with it. The first thing we need to know is the location of the neutral axis. So let me get the label up here. So we're going to locate the neutral axis relative to the bottom of the beam as indicated on the diagram by calculating y bar. We know that y bar is equal to the sum of y at I, a at I, divided by the sum of a at I, or a total. And so we can do that here. So let's break it down. We're going to do the flange first, then the web. So you'll recall our width is 150 millimeters and the thickness of the flange is 20 millimeters. And so what we need to do is to know the y at I, which is the distance from our datum, which is the bottom, to the centroid of that particular component. So that's half the thickness of the flange. So that's 20 divided by 2, so 10 millimeters. And then we do the transformed web. Remember, we're working from the cross-section on the right, which is the transformed cross-section. And so if I were to use its width, which is 9 millimeters, and its height is 150 millimeters. And so now all we need is the height from the datum again to the centroid. And so half the height of the web is 75 millimeters plus the 20 millimeter offset to make up for the thickness of the flange. And so we have a height of 95 millimeters. And then we just divide that through by area total, which is, of course, the sum of our two component areas. And we get a value of 36.38 millimeters for y bar. And so we're going to have to use that in our calculations, obviously. So the next calculation is for our moment of inertia. So let's use our space here. So to get our moment of inertia, we use the parallel axis theorem, which you'll recall is the sum of, and it's I at I, plus A at I, D at I, all squared. So working from the flange, and then we'll do the web. So we start off with our B, which is 150 millimeters. Our H, which is 20 millimeters, which is cubed divided by 12. So that's our I about its local axis for the flange. And then its area is the 150 millimeters multiplied by the 20 millimeters. And the D is the distance from the neutral axis to the centroid of the local component. And so our value there would be the 36.38 less half the thickness of the flange, or 10, so 26.38 millimeters. And that would be squared. And that's the first component. Now we have to do the same thing for the web. So we'll just do a plus, and our B of the web is 9 millimeters. Our height of the web is 150 millimeters. That has to be cubed, divided by 12. The area then is the 9 millimeters multiplied by the 150 millimeters. And then the D, and so the D here has to be the distance from the neutral axis to that centroid. So originally it was 95 millimeters up, but the centroid is 36.38 millimeters up. So you have to do the difference between the two, and that's 58.62 millimeters, and that has to be squared. And if we run that through our calculator, we should get a value for the neutral or the moment of inertia of 9.358 times 10 to the 6 millimeters to the 4th. So now we can go ahead and solve for the normal stresses at B, well, I guess it's B prime because it's on the transform section, and C, just using our flexure formula, so negative my over I, and those will be the stresses in the transform steel section. So let's go ahead and do that. And so we'll start at B. So our stress normal stress at B, so sigma sub B is equal to negative, that's obviously the moment, y to B over I, so that's negative. Our moment is given as 2 kilonewton meters, so that's 2 times 10 to the 6 Newton millimeters. And the distance then, y to B, so B is, or B prime, I guess we should be there. So our distance y to B prime is the total height, which is 170 millimeters, less y bar, which is 36.38 millimeters. And we divide all of that through by I, and I was calculated at 9.358 times 10 to the 6 millimeters to the 4th. And if we run those through our calculator, we will come up with a value of negative 28.6 megapascals, which of course for us is compression. Then we can do our normal stress at C. It's equal to same formula, negative my over I. The moment has not changed. And the distance in this case is equal to y bar because it's the distance down, but because it's below the neutral axis, it's negative, so negative 36.38 millimeters. And we divide that all through by I, 9.358 times 10 to the 6 millimeters to the 4th. And we run it through our calculator and we come up with a value of 7.78 megapascals. And positive indicates that it is tension, which makes some sense when you think about it, looking at it. So I'm going to go get an image which I've taken from the reference for the stress distribution, and I think you can see how that will all make sense. So let me go get that and I'll be right back. Okay, so with that image, we can see how the stress distribution would look here in our transform section. And we've just taken the values that we've calculated and used that to draw that diagram. And so the next and final step is to convert those stresses back to our original cross section, so the wood and the steel. And so let's go about doing that. So to do that, we have to convert from B prime to B, or from the steel back to the wood. And so the stress at B in the wood is equal to, and we use our transformation ratio again, so neta times stress B prime, and of course that's equal to our 0.06 for our transformation ratio, and the stress that we calculated at B prime, which was negative 28.6 megapascals, and we come up with a value of negative 1.71 megapascals. And of course, it's still in compression. And so with that, we can go about drawing or redrawing our stress distribution. The only thing we'd have to figure out is what the stress value is at the wood at the interface to the flange, and we're going to use some similar triangles to do that. And a little bit more space on the page, so I'm just going to roll that up. So let's figure out what the stress in the steel is at the interface, right? So it's still working from our transform section. So that's where our similar triangles come in. So stress at the steel. So the neutral axis, so where stress is equal to 0, is 36.38 millimeters up. and we're part the way down, so 20 millimeters from the end. So let's use our similar triangles. So on the top we have our 36.38 millimeters less the 20 millimeters in the flange, and that's our distance from the neutral axis divided by the total distance to the bottom, and we multiply that by the stress at the bottom, which was our 7.78 megapascals, and we come up with the value of 3.50 megapascals, still in tension of course, and that's going to be the stress in the steel at the point of interface with the timber. And to get the value in the timber, our stress in the wood is basically going to be our transformation ratio multiplied by that stress in the steel. So 0.06 multiplied by our 3.50 megapascals, and we get a value of 0.21 megapascals, again in tension. Now I'm just going to go get the last diagram from the textbook and stick it in here so you can see what that would look like. And there you go. You can see basically the stresses or the stress block in the wood is basically reduced by that ratio across the entire wood component, and you have a discontinuity where it goes back into the steel at the flange. And so that's how we use transform sections to manage composite beams. And let me just zoom out a little bit. You can see the whole solution top to bottom, and hopefully that was useful to you. It is a great skill to have. You'll see it again, particularly where we use reinforced concrete beams. We use transform sections quite a bit, so understanding how they work is really important. So hopefully that was useful to you, and we'll see you at the next sample.